Okay, so it's my pleasure to introduce Liang Dai as our speaker today. He did his bachelor's from Peking University in China, and then he was a PhD student in Johns Hopkins with Professor Mark Kamiankowski. After that, Liang was a postdoc, a member here, first was as a NASA Hubble Fellow and then as a John Bacall Fellow. He works on, and then after being a member here, he joined UC Berkeley as a faculty, where he is currently. Liang works on a lot of topics. If I go through them one by one, maybe I'll spend like 10 minutes of the talk, so I won't go. But then like some broad categories are cosmology, gravitational waves, and astrophysical lensing or gravitational lensing of astrophysical objects. And today is going to talk about newborn star clusters at cosmic noon seen through strong gravitational lensing.
Thank you for the introduction, and I'm really happy to come here because I left in the early stage of pandemic and I saw that everything has changed. I am happy to see like many old and new faces. So today I would like to tell you something about what we learned from cosmic noon galaxies with the help of strong gravitational lensing. So strong gravitational lensing really enhanced man-made telescopes' capability to see distant astronomical systems. So I have, like myself, have done a lot of study on the so-called highly magnified stars. But then recently there are also highly magnified star clusters discovered in these very distant galaxies in the young universe. So for a long time, I've been thinking what we can learn from these observations. So it was quite unexpected that the study I've been doing with some Berkeley folks seem to point us to the early chemical and dynamic evolution of these very massive star clusters within the first perhaps 10 million years. And then our analysis of spectroscopic data seem to establish a connection between such system and its self-chemical pollution. And that is related to this long-standing puzzle of multiple populations observed in globular clusters, the more evolved versions of these massive star clusters. So I would like to today I would like to tell you about what we have done and what we have learned so far. So to start with, I would just like to give some background introduction about superstar clusters and their more evolved version globular clusters. At least the people think globular clusters are the evolution outcome. And then what is this long-standing puzzle of multiple populations observed in almost all globular clusters with very peculiar chemical abundance patterns. And then I will present our spectral modeling of a gravitationally magnified superstar cluster candidate discovered in a cosmic noon galaxy. And then after we physically interpret the result, we find that the nebula surrounding that star cluster seems to be significantly chemically polluted. And then we think that this may have some connection with this puzzle of multiple populations. And then if there's time, I would also like to talk about another superstar cluster candidate, again found in the same galaxy that is even more difficult to understand. The reason is a very rare type of spectral phenomenon called Lyman alpha powered fluorescence of iron ions is discovered, and this we try to understand why this phenomenon happens and what does it tell us about the physical property of that star cluster candidate. So to start with, I think when we look at the Milky Way, we are immediately impressed by these extremely dense stellar systems called globular clusters. There are a lot of them orbiting today around the Milky Way, and typically they have like anywhere between 10 to the 5 to 10 to the 6 solar mass of stars. These are really, really old stellar systems. So therefore, logically, we think that there must be a beginning, right? Like at the very beginning, there must be a young star cluster called a superstar cluster that might have a mass between 10 to the 6 to 10 to the 7 solar masses. So here, just to show you how crowded the system is, this bar indicates the distance between the sun and its nearest neighbor. So you can see that we really have a lot of stars. But the difference is that for globular clusters nowadays, we only see the low mass stars that are still alive. But then there must be a version in the past that have a lot of massive stars. But then the naive picture would be that all the stars in the globular clusters, they form simultaneously and hence have exactly the same chemical abundance. But when people actually do detailed observation of individual stars, they find something quite unexpected. So basically, there seems to be some stars in the globular cluster whose abundance pattern matches what we would expect from the typical ISM abundance at a given metallicity. But then there are additional stars, and actually quite large in numbers, that show various that show very different chemical abundance. And this is first of all reflected in this kind of color magnitude diagram that we see multiple tracks, and then in this kind of color space diagram that we see multiple clumps. And then if you, when people measure the detailed abundance of some of the elements, they do find that there are correlated enhancement and depletion of these elements. So the most significant pattern is, for example, nitrogen and sodium are enhanced, and at the same time, carbon and oxygen appear depleted. And these two things seem to happen in a correlated way, not a random way. And then, for example, helium also is observed to be elevated. And then when people measure iron abundance, it seems that it's pretty uniform across the cluster, which suggests that this is not a different metallicity, but a rather anomaly in the chemical abundance pattern. And another thing in Berkeley found is that the total of carbon, oxygen, and the nitrogen seem to be more or less constant. There's no anomaly in the sun, which fits into this picture that the material probably is a hydrogen burning material that has undergone CMO processing. And then there are a lot of phenomenological results uncovered by studies over the years. So for example, people want to ask how does this anomalous population depend on mass and age of the cluster. So the general finding is that, first of all, the more massive the globular cluster is, it seems that the more significant this anomalous population called the second population is. And in fact, when for the most massive globular cluster, the second population in number can even dominate over the normal population. And the second thing is such anomalous population are never seen in open star clusters in the Milky Way, which have significantly less masses. And then when people look at the age, they found something very strange, that basically star clusters, whether or not it's very old or relatively young, as long as they are older than 2 gigayears, they typically show this second population as long as they are massive. But then when you look at systems younger than 2 gigayears, they don't see the second population. So these are some very intriguing observational facts. So
when we say that multi-population small in more massive cluster, is that already controlled by age? For example, we only see probably those old clusters that we see are only massive and low mass probably already disrupted. So
there are examples of massive younger systems. They are rare in the local universe, but there are such examples. And so far, there has been no clear detection as long as the age is younger than as we can see here in the plot. So there are some relatively massive systems.
You quoted masses for the superstar clusters, a factor of 10 higher than the masses for the globular. With a normal IMF, burn off of massive stars doesn't lose 90% of the mass. So where is all this extra mass going?
That's a good question. I choose not to give, I don't think I know this answer. I choose not to give. So that number is motivated by what we measure from that example. So I will show. That example is very massive. So of course, people have
some of the clusters show more than 2 populations, right?
Yes.
Say anything about that.
Yeah. So some of the clusters, they're just like more than 2 population. So, but then the thing is, it doesn't form a continuum. It seems to form some discrete clumps when you make a plot like this. So that is somewhat strange. Yeah, that's what I know so far. I do not at this point. I do not try to provide an explanation. So people have thought about possible explanations. So I will mention a number of ideas. So first, the people think maybe this has nothing to do with separate star formation out of chemically different material. Maybe this is because the original natal cloud, there is very special aerodynamics of the dust grains, so that these dust grains, they concentrate in part of the gas and they are diluted in some other part of the gas. And because the grains trap some of the metals, so then you get different parts of the natal cloud that have different amount of metals. But then this scenario has a major problem, which is you would expect enhanced parts of the cloud and also depleted parts of the cloud. So relative to the average abundance, it should be some kind of symmetric scatter. But what we see is more like a one-sided anomaly for each element. So this is a major problem. And then the other ideas, which are also kind of intuitive, is that some of the stars, they eject materials with this anomalous abundance. So for example, people think maybe these AGB stars, they within a particular mass range, they shed very slowly moving wings. And that operates when the cluster is around 30 to 100 million years old. The major problem of this particular scenario is that some of the correlation of elements is in the wrong direction. And there's the mass budget problem, namely, you may not have enough total mass to account for the observed amount of second population. And then the second thing is there are observational evidence in some systems that this is too late, because this would indicate at least the 2 star formation events separated by some significant amount of time. And then another idea is that maybe we have these very massive stars with masses larger than 1,000 solar masses forming from runaway mergers. And maybe these stars are extremely unstable and shed mass and pollute the intracluster environment. But this scenario is considered too speculative because we have never seen such stars. So any theoretical model is highly uncertain. Other ideas involve more massive stars. So for example, masses larger than 20 solar masses and do some job in the first 10 to 20 million years. So one idea is that maybe there are very fast rotating massive stars. So now the wind is fast along the polar direction, but they are slow along the equatorial direction. Maybe this material can be trapped. Although you have to do something with the timing so that you need to avoid the supernova explosion just clearing out all the gas. And then another idea which we kind of favor because of what we found is this so-called a non-conservative binary mass transfer. When you have two massive stars close to each other and one transferring mass to the other, at first the companion accepts some mass, but very quickly the companion spins up to some critical spinning velocity, at least on the surface, so that it's unable to accept a further mass. So then the transferred mass will escape the system through the Lagrangian point. And this scenario can also produce some slow ejecta, maybe that can explain the puzzle. And so there's a paper by Demink and the collaborators that they actually showed that using one example that they get the correct correlated chemical abundance anomaly. So I think there are so many, there are a number of ideas. Each idea seems to have some problems, some advantages, and a straightforward thought would be, let's just look at a young star cluster. And if we believe something special is happening, then maybe we can directly see it. But the problem is the star clusters that are massive enough to be globular clusters later, they are extremely rare to be found in our cosmic backyard. So in the Milky Way, these two clusters, Archer's cluster and the quintuplet cluster, they are only a few million years old, but they're extremely compact, but their mass is only order 10 to the 4 million, 10 to the 4 solar masses. And they seem to be surrounded by by thick gas, so that we can't see them in the UV or optical light. We could only see them in infrared light. So these are not massive enough to be globular cluster progenitors. And then this is so far my favorite JWST picture. It shows a famous star cluster R136 in the Large Magellanic Cloud. So this looks a very impressive system, but even this system only has 10 to the 5 solar masses. So again, not large enough to explain the more massive globular clusters. But then if we look further and further into nearby galaxies or galaxies in the local universe, we start to see more and more massive systems. So here I show some examples of, again, a few million years old, but then we start to reach between 10 to the 5 to 10 to the 6 solar masses. Many such systems, again, the problem is that they are deeply embedded in molecular cloud, so we can't really do UV or optical spectroscopy. But then when people compile all of these discoveries, put it on the phase space, mass versus radius, they find that basically as we look further and further, we just see more examples of young star clusters. Many of the points are globular clusters. They don't count, but some of the points, they're young star clusters, and they start to reach interesting masses, like a few times 10 to the 5 or even 10 to the 6 solar masses. So if you extrapolate this trend, you might surmise that if we look at high redshift universe, when the star formation activity is at its peak, there might be a much larger chance that we will find these systems. And in some sense, we have to have that because we see that nowadays globular clusters seem to be ubiquitously there around every major galaxy. So there must be a lot of such young systems in the young universe. So indeed, recent gravitational lensing observation, they found a lot of unresolved compact star cluster-like objects, and they might have masses ranging between 10 to the 6 to 10 to the 7 solar masses and be globular cluster progenitors. So we got interested in one example. This is a candidate star cluster in a lensed galaxy called the Sunburst, magnified by a foreground galaxy cluster. What is very remarkable is that this object shows a total of 12 highly magnified images located along this partial Einstein ring. And what is even more remarkable is that when people use a filter to allow only the Lyman continuum radiation, the redshifted Lyman continuum radiation, then suddenly everything else disappears from the field of view, but only these compact locations that show up. So this system apparently is leaking direct Lyman continuum radiation into the IGN, and it actually travel all the way to the Earth.
How do you determine the masses of these clusters? Just the line, like, is it kinematics or is it some?
So in simple words, they determine basically you even accounting for a very high magnification factor, higher value would be very unlikely from the lens modeling point of view. You still need the 10 to the 7 solar masses to explain the light because the system is really far away. Yeah, so you need a lot of stars to get the required amount of light.
So the closest analog, local analog to this might be the nuclear star cluster at the center of the Milky Way. And you didn't include that in your comparisons. Is there a reason that you left it out?
So the velocity dispersion of the system seems to be not very high, like around 50 kilometers per second.
So it doesn't have a black hole, a supermassive black hole.
And there's no spectral signature of any supermassive black hole. But I think that's a good question to ask. Could this be a progenitor of a nuclear star cluster? Okay, so then there's a lot of archive data taken for this object, including magnitude measurement in a dozen HST filters and also rest frame UV and optical emission line measurements. So then with Berkeley colleagues and also a grad student, Massimo Pascal, who leads the spectral modeling analysis, we are very interested to ask the question that can we build a physical model to explain all of these measurements, and then from that physical model we infer the properties of the system, including the star cluster sitting at the center and the photoionized clouds that must be surrounding the star cluster and are responsible for the observed nebula emission. So we want to do such a job. So just to quickly explain what has to be done. So basically, we first need to start with a population synthesis model of the cluster stellar output. And this, we have existing tools such as the VPAS model, which includes single stellar evolution and binary stellar evolution. And typically the model predicts that there will be some amount of non-ionizing radiation coming from the stars that dominates the total luminosity. And then there's also a significant amount of ionizing radiation if the system is young. And then this can be parameterized by, let's say, the metallicity of the system and the age of the system. And then the next step is that at least some fraction of the ionizing radiation will be reprocessed by surrounding gas, if the gas is optically thick to ionizing photons. And then we can use one of the popular photoionization code, Cloudy, to do the calculation. After the cloud reprocess this amount of radiation, what kind of spectrum we get. And then we choose a physical model parameterized by a ionization parameter U, which measures the ratio between incident radiation and the gas density. And then we take this physical picture that probably the cloud is isobaric. So then there's a total pressure parameter. So here's the physical picture. So the ionizing radiation comes in, and if the cloud is thick enough, only the surface layer is ionized, and that's where nebular emission lines are formed. And then the neutral part may not have a lot of processing of the radiation, but some of the starlight might be passing through this part if we are viewing from the back of it. And then eventually, if we combine the stellar light and the processed light, we apply a possible local ISM, that's the reddening, because that is also an unknown parameter. And then after we combine all of those, we get the observed spectrum. So then we choose to, when we model the nebula spectrum, we choose to do it more carefully, account for the geometrical dependence, because in principle, there can be several ways the observer see one of the clouds. So either the observer sees the illuminated side and exposed stars, or sees the exposed stars and the shaded side, or maybe some of the stars are obscured by the cloud, and we see the shaded side and the transmitted emission. So we think all of these possibilities need to be included into the model for the model to be physical. And then we choose to introduce
and also with stars inside the cloud.
That possibility so far we neglect, but we have some reason to argue that at least for that system, maybe this is not happening. So maybe I'll mention this a little later. So we introduce some geometrical parameter. For example, what is the fraction of clouds that cover around the cluster? Some fraction x between 0 and 1. And then maybe statistically clouds are not isotropically distributed, and maybe there are more clouds on the far side versus the near side. So we introduce a symmetry parameter. And then another parameter is like the obscuration fraction. Some of the stars may be exposed and other stars may be blocked by clouds. We know that at least some should be exposed because we see Lyman continuum radiation. So then you make a linear combination of all of these possibilities, and then that gives you the observed spectrum. And then there are some additional modeling details. First, we also want to take this opportunity to measure some of the element abundance. So for example, the baseline abundance would be rescaled solar, but then this will essentially set the ratio between oxygen and hydrogen. And then relative to oxygen, it might be that some of the elements may have some non-trivial abundance. So we introduce parameters to allow for that possibility. So the ones we can measure in this work is carbon, nitrogen, neon, and the silicon, just because of availability of lines. And then as we fit the data, we realize that there's a strong evidence that there's at least 2 populations of photoionized clouds. One with very high pressure, high density, and hosts ionic species of higher degree, higher ionization degree. The evidence for that is we have line ratio indicating that the electron density is at least 10 to the 5 particle per cc. That's very high. But then this population of clouds cannot simultaneously explain strong oxygen-2 emission, because oxygen-2 at high density will be suppressed, will be collisionally suppressed. So that's why we think there's strong evidence that there has to be a second population of low pressure, low density, and low degree of ionization.
So why does it have to be just 2 clouds and not a continuum of densities in photoionization regions and interfaces for all these clouds?
I think that is a good point, that it could be a continuum, but in that case, we don't know how to model it. So we choose to first compare, for example, 1 population versus 2 populations. Okay, so here I just show some of the results. It turns out that we can reasonably fit these HST filter magnitudes. And you can see some of the filters, they are dramatically enhanced above the continuum. It is because they include strong emission lines. And then simultaneously, it's a global fit. We can explain a number of line ratios and the absolute flux of lines. And here I try to show that for some of the lines, the solution says that the high pressure clouds dominate the luminosity, and for some of the lines, the low pressure ones dominate. And then there are additional lines where both might contribute comparable amount. So basically the bottom line is we find that the models can fit, and we are at least happy because it's not even obvious that the model can fit. Maybe the model will fail just completely. And then we go on to interpret the physical meaning of the results. So first of all, we do find that the model pins down the age to be around 3 to 4 million years. This is consistent with independent inference based on observed stellar wind feature. So basically the system seems to host a population of Wolf-Rayet stars. And then according to the templates, the age should be around 3 million years. And then we also find that there's no evidence, however we tweak the details, there's no evidence of significant ISM dust reddening. And then the metallicity is found to be somewhat like subsolar metallicity, not extremely metal poor. But then once we fix these intrinsic parameters, then in order to explain the light, we have to invoke a sufficient amount of stellar mass, assuming the standard IMF. And we find that even assuming a quite high magnification factor, we still need at least 10 to the 7 solar masses. 10 to the 6 solar masses is just not possible unless the IMF is significantly top heavy. The other thing we find is that the surface density of the star cluster, which actually is independent of the unknown magnification factor, is close to the empirical upper limit observed for arbitrary stellar systems in the local universe. So around 10 to the 5 solar masses per square parsec.
Sorry, do you understand exactly? Are you using different IMFs and trying to constrain?
Yes.
And how much evidence do we have?
So here the fiducial model is using standard IMF. We did try a top-heavy IMF, but then we find that almost all the intensive parameters, they are not affected. The reason is almost all the observables are dominated by massive stars. So that means whatever your IMF is, data just tells you how many massive stars you need. And then the amount of low mass stars, which dominate the mass, is just the extrapolation using your IMF. So we find that if you use a top-heavy IMF, then the biggest change is that you just predict a much smaller, let's say a factor of a few smaller cluster mass, but you actually don't, there isn't big change to these intensive quantities, such as age, metallicity, and the ionization degree of the clouds and so on.
Is SED a big factor? Like SED of stars, you assume something and the uncertainties in that, are they like significant?
Sorry, what uncertainty?
SEDs of stars?
A series. Oh,
the spectral energy of stars. SED?
the uncertainty in the SED.
Yes.
That we didn't include. We just take BPAS because we don't know how to quantify it. Is that what you're asking? The uncertainty.
I thought those were big.
Yeah, that is a good question. And some people do say that we can't predict the spectrum mass of stars. So that one, we just take the latest BPAS model as it is. So then, apart from the property of the star cluster, we can also determine the property of these photoionized clouds. And we said that there seems to be at least 2 populations with widely separated properties. So there are these nearby dense photoionized clouds that host higher ionization degree species, and the ionization parameter is high, and then the inferred density is inferred pressure is very high. So this pressure is actually quite remarkably high. And the reason we can robustly say this is because the sum of the line ratio, like this carbon-3 line ratio, tells us the electron density has to be 10 to the 5 particles per cc, and it's H2 gas, so the temperature is always around 10 to the 4 Kelvin, between 10 to the 4 to 2 times 10 to the 4 Kelvin. So that very tightly constrains the pressure. And then once we know the pressure, we know the ionization degree, we know basically what is the typical ionizing flux hitting the cloud. And then if we know the total size of the total mass of the cluster, then we can calculate at what distance you have to typically put these clouds in order to give you the required ionizing flux. And it turns out that apart from this magnification factor dependence, it should be around 10 parsec. So these clouds are pretty close given that the inferred mass is high. And then you can do the same thing for these low ionization, low pressure clouds. The density is lower and the ionizing flux is lower. So you have to put these clouds at larger distances, significantly larger distances. Very interestingly, when we look at one HST filter, which is dominated by one emission line, we do find that there seems to be a resolved component of nebular emission. So it seems that this picture, at least qualitatively, has some support from data.
Can I ask? So I appreciate the sketch, it's very useful to understand, but effectively when you do this, you really are thinking out certain, some slab geometry between the source and you, and then you're doing two different slabs with two different properties.
So basically, it's a slab, plane parallel slab setup under the assumption that the H2 region, because the density is high, so the H2 zone is very thin. So then, it's just like it's a plane parallel setup. You and P, it's something intrinsic of the photoionization cloud.
Okay, I guess my question is, if you go back to the sketch, what is the reasoning behind, how can you discern that the clouds that are denser and closer are actually smaller and patchy, so to speak? How do you come up with that picture?
Oh, that's a good question. That's what I'm going to say in the next slide.
Right, so
because in our model, we also have geometrical parameters. We don't assume that the entire solid angle is like covered by these clouds. So then basically, why it's not showing the same? It looks like it's stuck. Can you go back?
the other way.
Is it changing on your laptop?
Yeah, it is changing on my laptop.
Zoom Pro.
Oh, maybe I.
Oh, no.
Okay, so so we have this geometrical parameter, right? We have a number of geometrical parameters, right? We say that we allow some freedom that says these clouds only cover some fraction of the solid angle. Maybe they are not distributed symmetrically because the illuminated side and the back side has different spectrum for the emission lines. When we allow this possibility, we find that there's actually this global fit actually gives us some not a very, I would not say very tight, but interesting constraint on this geometrical parameter. For example, it says that these high pressure clouds should cover between 30 to 50% of the solid angle. And then these large distance low P clouds should cover between 10 to 30%. And then if you ask what is 1 minus this and that, which is the isotropic escape fraction, you find that it's around 10 to 15%. It's not very tight, but it is something.
Isn't there the degeneracy between the distance that you place the slab and the solid angle that is covering?
So, sorry, can you
I
repeat?
understand. So you have a slab at a given distance, and then you parameterize, what fraction of the solid angle is, being
So,
by this.
yes.
Is there the degeneracy between the distance of the slab and the size of the solid angle that you're covering?
So we didn't put the distance is not one of the parameter. The parameter really is what is the ionization degree of these clouds. And once that degree is fixed, then you say you have to put them at this distance in order to get the right ionizing flux. Because if you move it closer, it's more ionized, the nebular spectrum is different. If you move it further, it's less ionized, the nebular spectrum is different. So that constraint comes from that. Not from like we have any direct information about the distance. So, and then another very interesting thing is when we say what is the line of sight escape fraction, we get some higher fraction, like 35% to 75%. There's an independent work analyzing analyzing the relative ratio between observed Lyman continuum radiation and the UV radiation. And they conclude that there has to be a very high line of sight escape fraction between 40 to 90%. So what we are finding seems to be in agreement with that finding. And then the most interesting thing comes from chemical abundance. So as I said, we did allow some free parameter to measure carbon, nitrogen, neon, silicon relative to oxygen. And we find that carbon to oxygen, neon to oxygen ratio are not are unremarkable. They just look like some typical ratio that you would get from ISM gas at that metallicity. But then silicon is dramatically depleted from the gas phase. And we interpret that as these dense clouds actually in the gas, dust grains have already formed. So that's why the refractory species, they are depleted. Not only silicon, we find that the magnesium-2 emission are weak. The model predicts that they should be strong if all the magnesium is in the gas phase. And also the model wouldn't predict that iron 4 is very strong if all the iron is in the gas, but we don't see iron 4. So this is consistent with the picture that the gas actually is dusty. The second thing is there's a dramatic enhancement of nitrogen inferred from detection of this UV nitrogen 3 multiplet. This line is discussed in the literature at many places, but it has typically never been detected in a typical H2 region, typical star forming region. So typically this line is weak because nitrogen abundance is less than that of carbon and oxygen. But we detect a very strong nitrogen 3, which needs a factor of 10 enhancement in nitrogen. And then in order to test possible connection to massive star ejecta, we introduced two independent nitrogen enrichment factor for the high peak clouds and the low peak clouds. We find that the low peak clouds should not, there's no evidence that the low peak clouds is as nitrogen enriched. The reason is there are these nitrogen 2 optical lines that we have upper limits. At high density, these lines are collisionally suppressed, but at a low density, these lines should be very strong if nitrogen is highly enriched. So the detection of strong nitrogen 3, but non-detection of nitrogen 2 indicate that the closer gas are enriched, but probably the further gas they are not. So this hints at maybe the closer gas actually has a connection to massive star ejecta.
Sorry, so previously you mentioned that from like SED, there seems to be no sign of
Right, that's a good question. So there, the effect is coming from the host galaxy's ISM. So it's a two. So this that's actually this effect has almost no direct observational consequence. Well, it has some consequence, but it doesn't directly cause some emission because it's in the it's in the shaded side. Like the shaded side is very dusty, but if that is the case, you don't necessarily see a big change to the spectrum because the shaded side doesn't get energy input anyway. So it doesn't, it doesn't give you some. But this dust, what we are saying is the dense photoionized cloud seem to have refractory metals depleted. But the other statement is saying the host galaxies on the large scale does not seem to cause a lot of reddening. And then to put this in some context, right? So this is nitrogen to oxygen ratio as a function of basically metallicity. And then you find this clear correlation. There's some scatter, but the thing is, if you put the inferred 0.3 solar metallicity and the inferred enrichment is just way above here. So this is clearly a localized phenomenon. Like if you measure the integrated power spectrum, you just don't pick it up. Okay, so there's one interesting question. What can we estimate the total gas mass of the high P clouds? At first, this answer depends on the typical column density of the cloud. We find that unfortunately, current data doesn't allow us to direct constrain column density for the reason I mentioned. The interior is just cold, self-shielded, doesn't generate any emission. So there's no direct emission line probe of it. However, we think there is some dynamic consideration. In such an environment, the radiation pressure from the stars is extremely strong because it's a young system with other tens of thousands of massive stars. So the radiation pressure is extremely strong. So if there's nothing to counterbalance radiation pressure, then over a very short period of time, any such cloud should just be ejected from the system. They should not linger around the system. So then it becomes kind of fine-tuned that we happen to see a large chunk of them. Unless the column density is sufficiently large that the cluster gravity can balance the radiation pressure. And when you do a calculation, you find that the required minimum column density is log equals 22.5. So at this column density, there's a thin ionized layer and a significant neutral interior. And then if you do this, you find that if you take 10 to the 23 for the column density, you find that it's a few times 10 to the 5 solar masses for the gas. And if you calculate the nitrogen, total amount of nitrogen in that gas, assuming that it's fully mixed, then it's on the order of 100 to a few hundred solar mass of nitrogen. So curiously, this number, when the column density is 23, you find that this number is close, like smaller by maybe a factor of 2 compared to the total mass loss expected from the massive stars at around 3 million years. And this amount of nitrogen yield falls within the theoretically expected range of nitrogen yield. But then if the column density is actually larger than the gas mass is even larger, we run into problem. We will not have enough ejecta, we will not have enough nitrogen yield. But then maybe you can do this by saying that there's a mixture between massive structure, massive star ejecta and the natal cloud, some leftover natal cloud. If that is the case, maybe you can reach enough sufficient condition to trigger star formation in the shielded interior. But I think for this system, we seem to favor more like a column density 23 because of this argument. Okay, so what are the implications of this result? First is that it seems that because of high magnification, even for such a system at a cosmic noon, we can potentially get a lot of physical information by just doing careful spectral modeling. So I think this has not been explored in the literature. Typically people just do observation and present what they see, but they didn't try to try a bit harder to construct a physical model. So I think this is interesting. It means that potentially a lot of work can be done for these distant systems too. Even though naively you would think very little information can be extracted. So the second thing is it seems to point toward localized nitrogen pollution, but this object is just a randomly highly magnified system. So there's no reason that we are somehow lucky with this system. So this means that in the proximity of newborn superstar clusters, perhaps this phenomenon is common. And in fact, in the literature, we found that there are a nearby galaxy near a few superstar clusters, people found evidence of localized nitrogen enrichment. Now, what is the physical origin of the ejecta? There are several possibilities. One is that, could you have just wings from main sequence massive stars? I think the problem is, first, if it's unprocessed material, then the chemistry doesn't work. The chemical abundance doesn't work. And these main sequence stars, the wind is very heavy and very fast. So the gravitational potential cannot retain the material, cannot easily retain the material. The Wolf-rayet winds may work in terms of chemical abundance, especially the Wolf-rayet nitrogen type. But again, these winds are supposed to be very fast. So how do they stay in the potential is not clear. Could it be that there's the first batch of supernova explosion from larger than 60 solar mass stars, because that's the right timing at around 3 to 4 million years. But we think it doesn't seem to match data because supernova ejecta will produce a lot of oxygen and carbon, and that doesn't seem to, so then you would expect to get apparently high metallicity gas, and that doesn't seem to agree with data. Then that's why at the beginning I said this, either faster rotating massive star, the slow mass ejection on the equatorial plane, or binary mass transfer seems favored because you just get the right seems to get the right chemical pattern, and the ejecta is slow. So then you can more easily retain it, and then it also matches the pattern that if you have a low mass system, the gravitational potential is shallower. So then the thing will easily escape, and once you reach sufficient mass, you are able to retain the material. But I think the physical origin question is really an open question, especially how does the dynamics work is unknown. So how exactly the ejecta is retained in the cluster potential. And then some people suggest that even if you start with hot material, with a lot of kinetic energy, but the radiative cooling may happen very efficiently, that before the material blows out, the gas just cools and form very dense material and have very little momentum. So will that somehow contribute to this phenomenon? And then the other question is, even though in the naive picture, if you have a single high column density, radiation pressure cannot eject the cloud. But in reality, there must be a range of column densities, and there will be some peripheral part of the cloud that have smaller column densities. So in the literature, people suggest that it is from those weak line of sight that the radiation first just blow out the cloud. So over time, that might eventually just destroy these clouds. So can these clouds survive radiation the destructive effect of the radiation, that's not clear. So it seems that this is a radiation hydrodynamics problem. Basically, you need to account for the effect of photoionization, radiation pressure, gravity, and the cooling, radiative cooling. It can be very messy. So that's why I think we just present this empirical evidence that something like that might be happening in these clusters. But I think we do not so far fully understand the physics. So I don't think I actually have additional time to talk about this second thing, which is somewhat related, but not like entirely related. So maybe I can ask if you want to first ask some questions about this part or not.
Yeah, if there are any questions, please go ahead.
So do you see any even higher ionization lengths like C4, 1048 or?
That's a we don't see a clear detection of high ionization. Like the highest species is like neon 3 with 41 eV. Because the reason is at some point we were thinking, could there be some evidence of X-ray contribution to the ionization, but we didn't see like carbon, like strong emission from carbon 4 or nitrogen 5 or so on. So yeah, so the answer is no. In the spectrum, we didn't see that.
Be consistent with no 60 solar mass stars.
Sorry, consistent with
the fact that there is no stars with larger than 60 solar mass.
Because they have all died, you suggest. Oh, I see.
So about binary mass transfer, does that work for all kind of mass of stars? Because this system is so young, but if this mass transfer only happens like preferred for like low mass star, then actually, so it seems that there is some like constraint on like what type of binary or mass of the binary stars.
Yeah, to be honest, I do not yet know too much about it. So I showed this, so the main paper, I showed a example, they did the calculation, but that example is a 10 solar, I think it's a 15 solar mass versus 20 solar mass binary system. So I think at a 3 to, so here, they just showed some example what kind of chemical anomaly can be. But I think at 3 to 4 million years, such like they are normally would be called a massive system, but for our system, they are not really massive enough. And at 3 to 4 million years, they have not evolved of the maze sequence. So maybe there's no mass transfer expected.
And is your data like this enrichment imply like how many this kind of binaries you need to get a high?
My guess is that there must be like very high fraction, like order unity fraction of like these massive stars. Perhaps they are all in binaries of similar, like close to 1 mass ratio, and they all go through this process and eject a hydrogen burning material. Yeah, because you're right that there can be a mass budget problem. You need to, if the mass is so high, then you need enough systems to eject mass.
Are there other examples of this is a very special system, right?
Yes.
Are there other similar examples, maybe not as good, but where you can run this?
So I wonder, have people carefully looked at low nearby universe data? Because, for example, you can ask the question, which I do not know the answer to, like this fantastic JW, this is the first page. This fantastic JWST image, right? You see the star cluster, you see some gas. So is there such nitrogen enriched gas here? There should be some, like, there should be tons of data. So yeah, I don't know. Is it because people didn't look for it, or maybe there's nothing found? But you could argue that because the system is not as massive, so maybe the gas doesn't stay. But at least I think it's something curious to revisit the data, at least to see if either people have looked for it or people haven't.
Any more questions? I think like can you give like a lightning summary of in 2 minutes or something?
Oh, so basically this other system is very weird. We scratch our head for a long time and cannot declare victory, which is this system, first of all, has a lensing anomaly. 4 different modeling efforts suggest that object should have at least 3 to 5 counter images, but there's only 1. All the other are not detected. And that object is not a transient. The flux stays constant over 1 year in the rest frame up to % level. And if you look at the spectrum is completely consistent with the Young starburst. So that's why we think the system is a star cluster. But then the question is why we see this Lyman alpha pump, the fluorescent phenomenon. The only other example we found in the literature that shows this phenomenon is this famous massive star, Eta Carini. So people found that so this is some nebula that formed out of a 19th century eruption. But what people found is that there are some dense clouds just hundreds of AU from the star that seem to be slowly moving, and they have this fluorescent phenomenon. So then we think maybe this other system is just a larger version of this physics, like in the nebula property may be pretty similar, but then it's just, instead of having 1 star, you have like a very dense system of many, many stars. Yeah. So then the key question is, how do you make pumping work? The difficulty is that the Lyman alpha doesn't lie exactly on top of the iron line. There's about 300 kilometers per second detuning, but the velocity scale of the system is only 50 kilometers per second. So clearly some optically thick line transfer phenomenon is happening. But then the problem is, if the system has any significant amount of dust, Lyman alpha build up will not work, because Lyman alpha will immediately be destroyed. So that means somehow in that system, first of all, Lyman alpha can be very efficiently trapped. So it's like a leaky bottle that just builds up Lyman alpha intensity. Second, the system, for some reason, dust grains fail to form despite the inferred high density of the gas. So we think maybe our best guess so far is that you have a compact star cluster, and then there's some massive star ejecta that somehow do not escape the gravitational potential. They just sink to the bottom of the potential. And then the inner region is extremely cloud enshrouded. And maybe the radiation intensity is so high that dust is destroyed, but that's like more speculative. We don't have like a very detailed physical calculation. Yeah, so, but that system is again living in the same galaxy. So you could ask, how come there are double coincidences? First, it's weird spectroscopically. Second, it has a lensing anomaly. So how come that is the case? I think this is really, really puzzling.
Okay, let's thank Liang again.